Cycle 1, Lesson 9. In this lesson, we're going to move on to exponential and logarithmic functions. So just a quick recap of what an exponential function is. If the growth of a population is proportional to the size as the population grows, we describe it as exponential. So examples of exponential growth would be bacteria in a person or in a petri dish. Compound interest, that's a financial one. We can also have examples of decay where an exponential function goes downwards. Example of that would be exponential decay, as in what's it called, half-life. Also depreciation of values of vehicles. So we're going to look again how we graph exponential functions. That should be a review. And we're also going to talk about the inverse of exponential function. That's called a logarithm, although I don't think it comes up specifically in this lesson. The inverse of an exponential function is a logarithm, and we will be using logarithms in future lessons. The inverse of a function is when the input becomes the output. So this is just a reminder, by the way, of our of what an inverse is, because I don't think we've talked about it yet in this course. So remember, inverse undoes an original function. So I'm backtracking now. So it undoes an original function. So the input and the output switch places, which means that the x and the y values switch, since x is traditionally our input and y is traditionally our output. Graphically, this looks like a reflection in the line y equals x. Okay, so that's just a quick recap of exponential functions, since that's going to be something that we have to refer to in this lesson. All right, sorry, lost my train of thought for a second. Anyway, I'm back. Desmos investigation number 1, reviewing the basic function y equals b to the x. All right, well, so again, we know x and y are just variables, and y is our output, and x is our input, and b is just the base. It's what something is growing by. If something's doubling, then over a certain amount of time, for example, then our base would be 2. If it's tripling, it would be 3. All right? So base is our constant. It's related to our constant growth rate. Make a table of values and sketch the graph of the function y equals 3 to the x. So in this case, we're talking about something tripling here because of the base is 3. Well, let's start actually just by graphing it in Desmos. Let's get rid of a few things here. I think I can get rid of that. And let's open up Desmos. Okay, y equals 3 to the x. There we have it. Look familiar? Hopefully it does. We've seen that before in grade 11. And we can sketch that here. It's got a y-intercept of positive 1. It's got a horizontal asymptote of the x-axis, so it's never going to go below the x-axis or even touch it, and it's going to go up fairly steeply like that. It should be more of a smooth curve than I drew, but I won't try to fix that. So as far as making a table of values goes, if y equals 3 to the x, then that means that I'm going to put different variables on here. So I would have 3 to the negative 2. And just a reminder about negative exponents, that means 1 over the same thing to a positive exponent, so 1 over 3 to the positive 2. So that works out to be not 9, 1 over 9. So that's our y value. So we got this point, negative 2 and positive 1/9. And then for 3 to the negative 1, that's just going to be 1 over 3 to the positive 1, or just 1/3. I'm going to skip this one here. Maybe I'll come back to it, but for now I'm going to skip these 0.5 ones. I think they confuse things a bit. Let's go, though, to 3 to the 0. Remember what anything to the exponent 0 is? It's 1. 3 to the 1 is just equal to 3, and 3 to the 2 equals 9. So let's do the differences for these guys. And again, skip over those decimal ones. So the difference here, well, 1/3 is the same as 3/9. So going from 1/9 to 3/9 means it's got a constant difference here of 2/9. Can I get rid of this? Yes. All right. And then going from 1/3 to 1, it's going up by 2/3. And then from 1 to 3, it's going up by a difference of 3. And then going from 3 up to 9 is a difference of 6. The first differences are actually nothing for a rational function. First, differences work well for polynomial functions, but as you can see, there's nothing much going on for a rational function, sorry, for an exponential function. There's no, first differences don't mean anything for an exponential function. What we actually want for an exponential function is what's called the constant ratio. So the ratio between 1/9 and 1/3, if I just draw an extra line in here, call this ratio. Let's do this in red so it's a little different. So the ratio between 1/9 and 1/3, if I multiply 1/9 by 3, then I get a third, right? 1/9 times 3 is 3/9, and that reduces to 1/3. If I multiply 1/3 by 3, then I get 3/3, which is equal to 1. So the constant ratio, if I multiply each of these by 3, then I seem to be getting how I get from one number to the next. 3 times 1 is 3. 3 times 3 gives me 9. So we have this idea of a constant ratio instead. So we don't want to worry about differences. We do want to worry about ratios. And this constant ratio, by the way, is going to be the base of our power. Anyway, let's get back to what's written here. Horizontal asymptote, yes, y equals 0, the x-axis. Vertical asymptote, none, not applicable. All right, x-intercept, there isn't one. If it never touches the x-axis, then there can't be an x-intercept. Y-intercept, yes, y equals 1. And that's because for the y-intercept, we have to let x equal 0, right? Wherever the y-intercept happens to be, it's got to be on the y-axis. And any point on the y-axis has got an x value of 0. So if the x value has to be 0, that means that 3, or whatever the base is to 0, has to equal 1, because any base to an exponent 0 equals 1. So our y-intercept is always going to be 1, unless there's some sort of transformation going on. The domain is all real numbers. It goes on forever in both directions. The range is all real numbers as long as they are greater than 0. You can't touch the x-axis and it won't go below the x-axis. The end behavior, we have to use proper end behavior format here. As x goes towards negative infinity, so if we start at the origin and go this way, we can see that the y value is getting closer and closer to 0 from above. So y approaches 0 from above. If we start here and go it this way, we can see that as x approaches positive infinity, y is getting bigger and bigger. It's approaching positive infinity as well. Investigation 2, the exponential function and its inverse. So we want to graph y equals 2 to the x and x equals 2 to the y. So remember, we get the inverse of something by switching x and y. So if this is our basic function, then this, if we just switch the x and y, just switch places, x equals 2 to the y, will be the inverse of it. And we're going to expect that when I graph x equals 2 to the y, it's going to look like a reflection of y equals 2 to the x in the line y equals x. But let's actually do it and confirm that. Y equals 2 to the exponent x, and x equals 2 to the exponent y. It looks like that is the case. Let's be sure. Let's actually put in the line y equals x and see if there's a reflection there. It appears to be. Let's make that a dotted line just so it looks all fancy. All right. So the blue one is our function. The green one is our inverse by swapping x and y. It's been reflected in the line y equals x. Everything's as we expected it to be. So quick sketch. Here's y equals 2 to the x. Here's x equals 2 to the y. Let's do the domain of y equals 2 to the x. D equals XER. All real numbers. Range, all real numbers greater than or, no, just greater than 0. Asymptote is a horizontal one. Y equals 0, all right? Intercepts, yep, y-intercept at y equals 1. How many features? No. Okay, so I want to do the other one first to compare them. Domain of this one. All right, well, the domain for this one, it can't go below the y-axis. So the domain is any real number as long as x is greater than 0. The range, though, can go up and down forever. So there's no restrictions. There is an asymptote. The asymptote is the y-axis now, so x equals 0. And there is an x-intercept as well. The x-intercept is at 1, 0. So let's just say x equals 1. How are the features of the original exponential function the same or different from the features of its inverse? Well, in general, x and y have swapped places. Remember, the domain of the original function has become the range of the other inverse function. The range of the original function has become the domain of the inverse. The asymptote, the horizontal asymptote on the first one has become a vertical asymptote on the inverse, and the intercepts. The y-intercept has become an x-intercept. So all the things have just been, again, reflected in the line y equals x, and we switched x and y to make this happen. Investigation 3. Use sliders to explore the exponential and its inverse. What happens to the graph of y equals b to the x and its inverse for values of b for various things. All right, let's put this y equals b to the x and its inverse into Desmos. Y equals b to the x. And we'll add a slider for b. And we'll do x equals b to the y. Okay. When b is equal to 1, we don't actually have an exponential function. You may recall that exponential functions can't have a base of 1. Exponential functions have to have a base from 0 or greater than 0 and less than 1, or greater than 1. Because if it's equal to 1, this is what we get. This black line here is just a horizontal straight line, which isn't really exponential. But if I play with this slider a little bit, for example, say I increase it to 2, now we can start to see an exponential function and its inverse going on. So take a look at that. Now I'm supposed to increase it up to 4, right? So I'm going to watch as I slide it along. It's getting steeper. Both of them are sort of getting steeper. Well, the black one's getting steeper. The blue one's flattening out more, but they're both changing at the same rate. So there is what we have if we have y equals 4 to the x, or if we have x equals 4 to the y, because b is going to be replaced by 4 in this slider in each case. So we have a function that looks like this, and then we have its inverse, which looks like this in both these cases. Let's move down, let's not go over to the other side yet. Let's just go down and increase b to 10 and just see how it varies, how it's different. So I'll increase it gradually up to 10. So I'll drag it up, keep an eye on the black and the blue graph, see what's happening as I'm dragging this slider up closer and closer to 10. It's becoming steeper and steeper. Right? If I bring it back down, there it is at a very low 1.9, but if I bring it up, you can see it gets steeper, back and forth. Less steep, more steep. Less steep, more steep. Lower b value, greater b value. So they're the same, just more extreme when b equals 10. So it's got more of a sharp edge to it, sharp corner to it. And that's only because if the base is 10, it's going to grow faster. Okay, so there's that one. Same shape, different steepness. Now, if b is between 0 and 1, it's a decimal or a fraction between 0 and 1, let's see how that plays out. So, let's go, find 0. Let's go to, can't do 2.5 here, but let's go to 3 then. Okay, 0.7, very hard to move it such small amounts. Okay, there's 0.3, just slipped on me. Okay, there's 0.2. I'm going to go with that. So, now, again, imagine it's still reflected in the line y equals x. We still have the inverse going on. In fact, let's add y equals x in there again, just so we can see that it is, in fact, still a reflection. So in this line, the black one reflects over to the blue one across that line, and the blue one reflects over to the black one across that line, y equals x. So we got fairly steep when we have about 1/4, approximately 1/4. It wasn't exactly 1/4, but it looked a bit like this. And then the other one was going to look like this. The only difference for this next part is, again, it's got a different base. We're expecting something similar, but maybe more extreme because it's got a smaller number for a base. So as I switch from 0.2 to 0.1, there we go. Hard to see because, well, it's hard for me to see because I was so focused on getting exactly 0.1 with the slider, but it became a bit more steep. Right? Again, let's go back to 1, not exponential, but as I start to creep it down to lower and lower numbers, they're becoming steeper and steeper. 0 is not exponential. That's why the graph disappears once I hit 0. But 0.1 is steeper than 0.2 or 0.3 and so on. They probably don't look much different in my sketches, but, you know, they're supposed to be a little bit more extreme as the numbers get either closer to 0 for the decay ones, and these ones are all called decay, And as the numbers get bigger for the growth, these are all called growth. All right, here is a collection of key concepts which you can read over on your own. I won't read it to you, but that's it for our introduction to exponential and their inverse.